13.1 Exponential growth functions. How is the graph of g of x equals a times b to the x minus h plus k, where b is greater than 1, related to the graph of f of x equals b to the x? Well, the A, like in the past, gives a vertical stretch or compression, and then H, again, like with the others, moves left or right. And K moves up or down. Graphing and analyzing f of x equals 2 to the x and f of x equals 10 to the x. An exponential function is a function of the form f of x equals b to the x, where the base b is a positive constant other than 1, and the exponent x is a variable. Notice that there is no single parent exponential function because each choice of the base b determines a different function. So let's try. F of x equals 2 to the x, so 2 to the negative 3 equals 1/8. 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the first power is 2. 2 to the second power is 4. And then 2 to the third power is 8. Same thing over here. 10 to the negative 3 is 1/1000. 10 to the negative 2 is 1/100. 10 to the negative 1 is 1/10. 10 to the 0 is 1. Might want to pay attention to that right there. And then 10 to the first power is 10. 10 squared is 100. And then 10 to the third power is 1000. Graph the parent function f of x equals 2 to the x and p of x equals 10 to the x by plotting the points. The first one we had was negative 3 and 1/8, and that might be like right there. And then negative 2 and 1/4 might be about right there. Negative 1 and 1/2 we'll say is right there. 0, 1 right there. And then 1, 2, 2, 4, and 3, 8. And it might look something like this right here. All right, let's try the other one. Negative 3, and then that's 1/1000. That's real close. I can't get that close. And then negative 2, and that's 1/1000. That maybe. And then negative 1 would be 1/10. 0, 1. 1 would be 10, which is off the charts here. Maybe right there. Maybe right there. And then, and I can't draw it that close. Okay. What do these two have in common? Look at them. They both have that point 0, 1. Okay, that point 0, 1. What is the domain of each function? What is the domain? The domain of f of x equals 2 to x is, and look back at the graph. It goes, it gets to negative infinity real quick. And then it also going up, it gets to positive infinity real quick. So the domain is going to be x such that negative infinity is less than x, which is less than positive infinity. And the domain of p of x is going to be the same thing. But it will get there even quicker than f of x. What is the range? The range of f of x is y such that, and y, it goes up, right? It goes up. But where does it start at? The range of f of x. Look back at the graph. Look back at the graph. What is the range? It's just here above 0, right? And it goes up. But it doesn't actually touch 0. So it's going to be y is greater than 0. And then the range on p of x, it does the same thing. It does the exact same thing. So again, it's going to be y is greater than 0. E, what is the y-intercept of each function? The y-intercept of f of x equals 2x is 1. That's where it crosses the y-axis. Same thing with p of x. It crosses the y-axis. What is the trend of each function? In both f of x and p of x, as the value of x increases, the value of y increases. Reflect. Will the domain be the same for every exponential function? Yes. Yes. Because the value of the exponent x can be any real number. Two, will the range be the same for every exponential function of the form f of x equals b of x, where b is a positive constant? Yes. Because the value of b to the x power, where b is a positive number greater than 1, will always be a positive number. Will always be a positive number. Will the value of the y-intercept be the same for every exponential function, y or y not? Yes. Because a non-zero base raised That looks like an n, raised to the power of 0 is always equal to 1. Graphing combined transformations of f of x equals b to the x power, where b is greater than 1. A given exponential function g of x equals a times b to the x minus h plus k with base b can be graphed by recognizing the differences between the given function and its parent function f of x equals b to the x power. These differences define the parameters of the transformation, where k represents the vertical translation, h is the horizontal translation, and a represents either the vertical stretch or compression of the exponential function and whether it is reflected across the x-axis. You can use the parameters in g of x equals a to the b to the x minus h plus k to see what happens to two reference points during a transformation. 2 points that are easily visualized on the parent exponent on the parent exponential function are 0, 1, and 1b. In a transformation, the point 0, 1 becomes h, a plus k, and 1b becomes 1 plus h, and then ab plus k. Write these down. These are very, very useful. Very useful. They make graphing the transformations very easy. The asymptote y equals 0 for the parent function becomes y equals k. The graphs of f of x equals 2x and p of x equals 10x, 10 to the x power, are shown below with reference points and asymptotes labeled. Example 1. State the domain and range of the given function, then identify the new values of the reference points and asymptotes. Use these values to graph the function. Okay, you go ahead and follow through A, and when you get back, we'll do B together. Q of x equals 1.5 times 10 to the x minus 3 minus 5. The domain of Q of x equals 1.5 times 10 to the x minus 3 minus 5. Okay, so the domain, and we said this earlier, the domain is always going to be negative infinity is less than x is less than positive infinity, always. The range of Q of x equals, and the range will always be, if A is positive like this, it will be y such that y is greater than k. Okay? So here, if A is positive, it will always be y such that y is greater than k. If A is negative, it would be y such that y is less than k. Always. Examine Q of x and identify the parameters. So what do we got? We have A is 1.5. And we have H is 3. And K is negative 5. Okay. All right. This will make it easy. The point 0, 1 becomes H and then A plus K. H, we said, is 3. 3. So that will give you 3. And then A is 1.5 minus K. 1.5 minus 5 will give you negative 3.5. And 1b becomes 1 plus h. 1 plus 3 is going to be 4. And the y value will be ab plus k. A times b, that's 1.5 times 10, which is 15 minus 5. That gives you 10. The asymptote becomes y equals k. Well, k is negative 5. So the asymptote will be y equals negative 5. I think we're supposed to graph it now. Let me scoot that up a little bit. Let me scoot that up. So my asymptote here is negative 5. So that's going to be down here. Not 2, 4. So that was. You got to watch your. And then we had a point at 3, and then 3 and negative 3.5. So 3 and negative 3.5. That's going to be like it's going to be like right there. And then we had a second point at 4, 10. That's going to be about right there. So it's going to go something like this right here. Missed that one. Smooth that out a little bit. So, and there it is. Your turn. So let's take a shot at it. Let's take a shot at it. Okay. A. What is A? A equals. Let me do it like this. A equals 4. H equals negative 2. And then K equals negative 6, right? So our domain, and we said our domain is always x such that negative infinity is less than x is less than positive infinity. And our range, we said our range will be y such that, now a is positive, so that's going to be y is greater than, and then what is our k? Negative 6. Okay, which that also gives us our asymptote. So our asymptote is y equals negative 6. So let's find negative 6 over here. Let's go ahead and graph that. All right, there's our asymptote. A is positive, right? Okay, so we have that point 0, 1. 0, 1. And remember, we said that is always H, A plus K. All right, so what is H? What is H? H is negative 2. So this will be negative 2. And then A is 4 plus -6, that's going to give you -2. All right. So let's plot that. What do we got? -2, -2. That's going to be right there. Okay. And then we have 1b. 1b. And that's always going to be 1 plus h, and then ab plus a times b plus k. All right. So 1 plus h, that's going to be 1 plus -2. That's going to give you -1. And then a times b, a is 4, b is 2 right here. Remember, this is your 2. This is your b. So 4 times 2, that's going to be 8 plus k. 8 plus -6, that's going to give you +2. So we're going to have a point -1, 2. -1, 2. And that's going to be right there. Okay? So we're going to have a graph and it's going to look something like. Try to draw that fairly smooth. And there you go. 5. Let me move that up a little bit. 5. Okay. So what do we know? Well, let's see. What's our domain? Domain. What is our domain? It's always x such that negative infinity is less than x is less than positive infinity. What about the range? What about the range? Okay, we need to check. Okay, a is negative, so that's going to be y such that y is less than, and what's k? K is 3. And that gives us our asymptote. Our asymptote is y equals 3. So let's find 3 here. Let's go ahead and graph that. So what do we know? Well, we know k equals 3. We know that h equals -2. And we know that a equals -3/5. All right. So our first transformation, 0, 1. Remember, 0, 1 is always h and then a plus k. H and a plus k. And that's going to become, well, what is h? H is -2. -2. And then a is -3/5 plus k. So we got -3/5 plus k is 3. So that's going to be -3/5 plus, and we'll make that, that'll be 15/5, which is, that's going to be 12/5, positive 12/5. So we're going to have 12/5 here. So -2, and then 12/5. Right about in there, we'll say. All right. And then 1b, remember that's always 1 plus h, 1 plus h, and then ab plus k. And all right, so 1 plus h, what is h? H is negative 2. 1 plus negative 2 is negative 1. And then A times B, okay, I better do this over here. A is negative 3/5 times B, and B in this case is 10, times 10, and then plus K, and K is, so it's going to be plus 3. Now, if memory serves me correct, 10 goes into 5 2 times. So now we got negative 3 times 2, that's negative 6. Negative 6 plus 3 is going to give me negative 3. So we got negative 3 over here. Okay. So let's find negative 1, negative 3 is going to be about right there. Okay. So we got, and then it takes us nosedive almost. And then like that. Around that a little bit better. Yeah. You get the idea. All right. Moving along. Writing equations for combined transformations of f of x equals b to the x power, where b is greater than 1. Given the graph of an exponential function, you can use your knowledge of the transformation parameters to write the function rule for the graph. Recall that the asymptote will give the value of k, and x, and the x-coordinate of the first reference point is h. Then let y sub 1 be the y-coordinate of the first point and solve the equation y sub 1 equals a plus k for a. Finally, use a, h, and k to write the function in the form g of x equals a times b to the x minus h plus k. All right, example 2, write the exponential function that will produce the given graph using the specified value of b. Verify that the second reference point is on the graph of the function. Then state the domain and range of the function in set notation. So I'll let you do A, and when you come back, we'll do B together. So we're gonna let B equal 10. The asymptote is y equals, and you can see, look here on the graph, y equals 6, showing that k equals 6. And I better use, let me use pink. I've been using pink. 6. All right. The first reference point is negative 4, 4.4. This shows that h is negative 4, and that a plus k is 4.4. Substitute for k and solve for a. So a plus k is 4.4, and then a plus 6 equals 4.4. If we subtract 6 from both sides, we get a equals negative 1.6. So if a is negative 1.6, b is, or h is negative 4, and k is 6. Substitute these values in the q of x to find q of x. Okay, so a is negative 1.6. It said b was 10 right off the bat. And then you got x minus negative 4, and then k plus 6. So if you were to write it, it should look something like this. G of x equals negative 1.6, and that's going to be x, and 10x plus 4, and then plus 6. All right, good. Verify that q of negative 3 equals negative 10. Is that going to, let's see. So q of -3 equals, and that's going to be negative 1.6, and then that's going to be, put the -3 in for the x, and that's going to be minus -4 or +4, and then 6. Okay, so you got negative 1.6, and -3 plus 4 is 10 to the first power. So that would be 10 to the first power. And then plus 6, write that a little bit above that, plus 6. Okay, so you got negative 1.6 times 10 would be negative 16 plus 6, and that will give you negative 10. So the domain of q of x is x such that negative infinity is less than x is less than infinity. And that's the domain. And the range is going to be y such that y is less than 6. It's going to be underneath the asymptote. All right, our turn. Write the exponential function that will produce the given graph using the specified value of b. Verify that the second reference point is on the graph of the function. Then state the domain and range of the function in set notation. All right, so what do we got here? Well, the asymptote, and you can see it gives you the asymptote, and that's going to be y equals -5/2, and that tells you that k equals -5/2. Okay. Now we have this point 3, -1. 3, -1. Okay. Now what do we know about that? Well, three -1. Think about it. That's 0 negative. That's supposed to be 0 -1, which is h and then a plus k. So this is supposed to be h and then a plus k, right? Okay, so that gives us something. That says that h equals 3. Now a plus k, okay, so we got a plus k equals -1. Now we know that k is -5/2. -5. We know that k is -5/2. -5/2. So that's really a minus 5/2. So if we add 5/2 to both sides, if we add 5 plus 5/2 and then plus 5/2. Now, -1, wouldn't that be -2/2 plus 5/2? So, see where I'm going with this? This is going to give you a. A will equal -5/2 plus 5/2. That's going to give you 3/2. So a is 3/2. So now we have our 3 points. 3/2. And we can write our equation, and we'll just call it g of x. G of x equals, and that's going to be 3/2 times, and it gave us a b of 2. That's going to be 2, and then x minus h, which is 3, and then plus k, or minus 5 halves. Minus 5 halves. Okay, now it gave us a checkpoint here, 4 1/2, right? So we're saying that g of 4 equals, and then we got 3 halves, and that's going to be 2, and that's going to be 4 minus 3 minus 5 halves. Okay, so g of 4 equals, and that's going to be 3 halves, and that's going to be 2 to the first power minus 5 halves. Okay, minus 5 halves. And I'm looking, these two will cancel out. So I got 3 minus 5 halves. Now 3, that's like 6 halves, right? 6 halves minus 5 halves. And that's going to give me 1/2, which is what I was looking for. Okay, so they do verify. They do verify. Now it's a party. Modeling with exponential growth function. An exponential growth function has the form f of t equals a to the a times 1 plus r to the t power, where a is greater than 0 and r is a constant percent increase expressed as a decimal for each unit increase in time t. That is, since f of t plus 1 equals 1 plus r times f of t equals f of t plus r times f of t, the value of the function increases by r times f of t on the interval t and t plus 1. The base 1 plus r of an exponential growth function is called the growth factor, and the constant percent increase r in decimal form is called the growth rate. Find the function that corresponds with the given situation, then use the graph of the function to make a prediction. Tony purchased a rare guitar in 2000 for $12,000. Experts say that that its value will increase by 14% per year. Use a graph to find the number of years it will take for the value of the guitar to be $60,000. Write a function to model the growth in value for the guitar. F of t equals a times 1 plus r to the t power. So if a, what he paid for it is a, and that's $12,000. They said it would grow by 14%. So you'll have $12,000 or 12,000 times 1.14 to the t power. Use a graphing calculator to graph the function. Okay, let's see here. Yeah, just so happens I did that. So 12,000, 1.4, and that's this blue in here. It crosses just like that. Looks pretty cool, doesn't it? And then what did it say? Let's see. Let's go on. Use the graph to predict when the guitar will be worth $60,000. Okay, it says use the trace function. I know an easier way. So here's the graph. This blue one here is the graph. And if you'll notice, menu 4, 1, I changed the settings. I put -1 for the min, 20 for the max, and an X scale of 2. For the Y min, I put -1 and 80,000 on a scale of 5,000. Okay, so I could take a look at it. Now, if I want to know when it's going to be worth 60 grand, I can press tab and put 60, 1, 2, 3 in there. All right, so there it is. And what I'm going to do, menu 6, 4, I'm just going to find that intersection between that graph and that graph. And I see here, it's going to take 12.3 years. 12.3. All right. And so the guitar will be worth worth $60,000 about 12.29 years after it was purchased. Not a problem. At the same time that Tony bought the $12,000 guitar, he also considered buying another rare guitar for $15,000. Experts estimated that this guitar would increase in value by 9% per year. Determine after how many years the two guitars will be worth the same. Okay, so write a function to model the growth in value for the second guitar. So A is the initial value, which is $15,000. And, well, those are terrible looking zeros. 0, 0, 0. And then 1 plus, and it says it's going to grow by 9%, so 0.09. So my equation will be 15,000, and then 1.09 times 1.09 to the t power. So use a graphing calculator to graph the two functions. And you'll see I did that right here. See where 15,001 and then that one there. And okay, so we did that. Use a graph to predict when the two guitars will be worth the same amount. Okay, where they cross, that's where they will equal, and that's this point right here. Okay, and I found it by menu 6.4. And it says 4.98. 4.98. G of t equals 4.98, or well, when G of t equals f of t. And so the two cars will be worth the same amount in 4.98 years after 2000. So in 2005, they will be worth the same amount. Reflect. In part A, find the average rates of change over the interval 0, 4, 4, 8, 8, 12. Do the rates increase, decrease, or stay the same? So that was part A. Part A. So 0, 4, right? So where was it at 0? And let's go over here. Let's go back. And then we're doing this graph right here. So I think what I need to do is I need to clean some stuff off. Okay. Control, clear, enter. I got rid of that. Tab. That's something else. That's something else. And let's get rid of that. Control, clear. Okay, so now that I just got this right here, so I'm going to hit Control T. Okay. So 4 gave me 20,267. Open that up a little bit. And then that way. Yeah, so 20,267 and 52. And 0 was 12,000, right? Okay. So this is going to be 20,667, 267, 20,267, 267.52 minus 12,000 all over 4 minus 0. And that's going to give me $2,066.88. 88 cents. And then 4.8, and then I'm, I did the same thing. I just 4, and then went down there to 8, $34,231.03. Okay, so this is going to be, what are we going to have here? 231.04, got to round up, 04 minus, and that was at $20,267.52. And now we have 8 minus 4, put that in your calculator, and you should get $3,490.88. And then the last one was the interval 8, 12. And I did the exact same thing. And for 12, I got 57,814.86 minus 34,231.04. And then that's going to be 12 minus 8. And again, put it in my calculator, I got $5,895.96. Do the rates increase? Yes, they increase. Okay, so the guitars are they are getting increasing in values. Increase for values of X. So as time goes on, the two guitars get more valuable. Your turn. Find the function that corresponds with the given situation, then graph the function on a calculator and use the graph to make a prediction. So John researches a baseball card and finds that it's currently worth $3.25. So A equals $3.25. And I think we've been using red for that. So A equals $3.25. Okay. However, it is supposed to increase in value by 0.11. Okay. So B, we'll use a different color. B is going to be 1 plus 0.11 or 1.11. In how many years will the card be worth $26? Good question. So our equation is going to be f of x equals 3.25 times 1.11 to the x power. And we want to find out when it's going to be worth $26. So f of 26 equals 3.25, 1.11 to the 26 power. And you know, there's an easy way to figure that out. You can put it in your calculator. Let's see, Control T. And I graphed it, and there it is, 3.25. And I want to know when it's worth $26. So I'm going to press Tab, 26, enter. I'm going to find that intersection, menu, 6, 4, and it will be worth that in 19.9 years. 19.9 years. That's a little while to wait. How are reference points helpful when graphing transformations of f of x equals b to the x, or when writing equations for transformed graphs? The points of the parent graph are affected in the same manner. By shifting each reference point by the same value or ratio, then the transformed graph can be drawn. So, because the points of the parent graph are affected in the same manner. By shifting each reference point by the same value or ratio the transform graph can be drawn. Give the general form of an exponential growth function and describe its parameters. That would be f of x equals a times b to the x power. A is the initial value, initial value, and it should be, well, it has to be greater than 0. B is the growth factor. And it should be greater than 1. Essential check-in. Which transformations of f of x equals b to the x change the function's end behavior? Let me move that up. Okay, which ones change its in reflections across the x-axis? Let's see. Reflections across the x-axis change the function's end behavior by making the reflected function increase toward the asymptote as x approaches negative infinity and decrease towards negative infinity as x approaches infinity. Reflections. Okay, so you've got, what do they look like? Okay, normally they look something like this right here. Okay, and then you got some point. And then it goes like this. So what's the end behavior? As x approaches negative infinity, f of x approaches 0. As x approaches positive infinity out here, f of x approaches positive infinity. So what changes the end behavior? If you reflect it over the x-axis, it'll look something like this right here. Okay, what happens here? As x approaches negative infinity, f of x approaches 0. As x approaches positive infinity, f of x approaches negative infinity. Now let's see. Which transformation changes the function's y-intercept? Which transformations change the function's y-intercept? Vertical. Let's see. Let's do that. We'll do this. We'll do this one here in blue. Which let's see. Which transformation changes the function's y-intercept? Vertical translations. That's the k, when k is not equal to 0. It moves it up. Horizontal translations. They move it left and right, which that affects where it crosses the y-axis. Vertical stretches and compressions can. So vertical stretches and compressions. Reflecting it across the x-axis, reflections across the x-axis, as you saw right here in that graph right there. They all affect the location of the y-intercept. All right, good. Great lesson, folks. Thank you very much. I'll see you in school tomorrow, and have a great evening.